In Module 6, we look at the timer peripherals, which are an essential part of any microcontroller that allow us to measure time delays or measure events, generate pulse width modulated signals, and so forth. So in this module, we look at the timer peripheral concepts and also input capture for measuring timing of input signals, output compare for generating pulse width modulated signals and other signals. And we also look at using timers with state machines in order to create time delays. So this is an extension of the scheduling discussion that we began earlier. In this part, we're going to talk about the timers. And we give an introduction to the timer peripherals in the PIC32 microcontroller. And students see the concept of the timer being a timer with a 16-bit comparator that compares the timer value against a period value. And this allows us to count a certain number of events or a certain amount of time or generate a signal with a certain frequency. We learn about the timer registers, clock sources, clock source prescaling, and also generating interrupts with timers. The demonstration code for this, Demo 6 Timers Flashing LEDs, is used to show how to flash an LED using a timer which generates an interrupt every 1/10 of a second. So the LED is toggled 10 times a second, so the LED will be flashing at a rate of 5 Hertz. So here is the demonstration code, Demo 6 Timers Flashing LED, and within the user code we see initialization of the timer, we see the interrupt service routine, which simply toggles the LED, and the initialization code, and we also see the main code, which after initializing the application just sits in an infinite loop. The ISR does all of the work. So we can build this code, and after loading we can program it into the MCU's flash. And with programming complete, we see the LED is flashing at a rate of 5 Hertz. So let's take a look at the code that was used to generate this. So in this code, we have the main function, which calls init app, which initializes the peripherals, including the timer. Here's our while one loop that just sits there. So the main function does nothing. It's just the interrupt service routine that's going to execute. And here is the interrupt service routine, toggling the LED. So we're toggling LED 2. Here we introduce the idea of a static variable. So that's a variable that retains its value from one call to the function or the interrupt service routine to the next, but it's not visible outside. And we also show the concept of a sequence diagram where we have various actors. In this case, we have software, the main function, and the interrupt service routine for timer 2. And we also have hardware with the timer 2 peripheral and the LED. So we can see the main function starts timer 2, which is going to count up from 0. And it will generate an interrupt when it gets to a certain value, period 2. That will generate an interrupt, or that interrupt will cause the interrupt service routine to run and toggle the LED, so the LED turns on. After the next time period, another interrupt is generated, the interrupt service routine runs again, the LED is toggled off, and so forth. This gives the students an idea of the interaction between hardware and software and the sequence of those interactions. In the timer module, we also look at how to use the timer peripheral to help with scheduling. And we're going to look at using the timer module to cause time delays in hardware rather than software to help out with our state machine scheduling. If you remember, the LED scanning example has 2 tasks, one which scans the LEDs and the other which pulls the switches. And we split the LED scanning up into 4 individual states. And the finite state machine executes one of those states per call. Here's the source code for this. And you can see that after driving the LED, we call a delay function. So this is just wasting CPU time. It's sitting in a loop, not doing anything other than trying to count up to whatever this number is. That's an ineffective and inefficient way to use the processor. So in this module, we look at how to use a timer to generate that time delay instead. What we're going to see is that this works just as well as the previous version, but with much less CPU overhead. So we open the project Demo 6 Basic Concurrency Task Timers, and we can build it. And then we can program the microcontroller. And now that it's done programming, we can see the LEDs scanning along. When we press the fast switch, they scan faster. When we press the blank switch, they turn off. So the system is still working. Let's take a look at the source code. Here we have our read switches task. And instead of setting a shared variable called gled scan delay, which the delay loop uses, we're going to replace that by loading up the timer 2 period register, PR2, with the right delay value. So here, PR2 equals fast period, or PR2 equals slow period. So these two lines of code are configuring the timer to run at a faster or slower speed. This is still task code, so it gets sampled whenever the task runs. The code to scan the LEDs could be either in an interrupt service routine or it could be in task code. And this introduces trade-offs that the students can consider about how to implement this. We could put the state machine into the task code, and in that case, our scan LEDs with task function looks like this. And we may call the task scan LEDs function if run task scan LEDs is set. So this is a flag that gets set based on whether we want to scan the LEDs. Or we could put the state machine in an interrupt service routine, in which case the scheduler code doesn't need to call that at all because the interrupt service routine will handle that for us. We also introduce how to communicate between the interrupt service routine and the task code. So we look at having a global variable, a flag, that the interrupt service routine can use to request for the main function to run the task to scan the LEDs. So in this case, the interrupt service routine, each time it runs, will increment this run task scan LEDs variable, and this scan LEDs with task function is acting as the scheduler, and if it's been requested to scan the LEDs, it will do that and then decrement the variable that indicates how many times it's been requested. So this is one mechanism for communication between the interrupt service routine and the mainline code. We could put the state machine into the task if we want, and in this case, we've got a different set of design trade-offs to consider. Here we see what the state machine looks like in the interrupt service routine, and we have to deal with communication and static variables. These are useful for the students because they see multiple ways of solving the same problem, and by doing that they see the pros and cons of the different approaches, and it gives them a much stronger learning experience.